Good day. For those of you who don't know me, my name is Douglas Harder, and this topic we're going to discuss augmented matrices. So in this topic, we will define augmented matrices. We will show how operations on systems of linear equations have a corresponding operation on these augmented matrices. And then being able to use these augmented matrices to find a solution to the linear equation, we will then discuss some of the benefits of using augmented matrices as opposed to using systems of linear equations. Let us start with either a system of linear equations or equivalently a linear combination of vectors equaling a given target vector. In the second case, the vector b is simply the right-hand side of each of the linear equations, and the vector a sub j are the coefficients of x sub j in each of the corresponding equations. Now, given a system of linear equations, we may define the corresponding matrix A, that is, the coefficients of the various unknowns. Let us subsequently augment that matrix by appending on the right-hand side the vector b. So the notation here is as follows. The matrix A is already a matrix. However, the dotted line indicates that we are now going to append, in this case, a vector b to the right-hand side of the matrix. So this dotted line is going to help us understand that we are appending or augmenting the right-hand vector b into this new matrix. If, of course, the matrix A was m by n, the augmented matrix will be m by n plus 1. Now, it's important to remember that while matrices will have a significance beyond just the coefficients, the only purpose of the augmented matrix is to help us systematically find a solution to a system of linear equations. That is it. That is, the augmented matrix is a data structure and not a mathematical object. For example, let's suppose we have a system of linear equations we're trying to solve. Here's one such system. Now, we could write this system as an augmented matrix. All right. Now, if we are actually going to go back to this system of linear equations and solve it, we would now add -4 times equation 1 onto equation 2. And that would yield the following system of linear equations, one that is equivalent to the one above. Notice that we can also write down the augmented matrix corresponding to this new system of linear equations. All right, now from here we can deduce that x2 is equal to -0.6. However, suppose that we did not have the equations, and instead we only had the two augmented matrices. Well, could we not instead add -4 times row 1 onto row 2 in order to get the second augmented matrix? And from that second augmented matrix, may one not deduce that x2 is -0.6? That is the approach we will take. As a second example, consider this system of two equations in 4 unknowns. Again, here's the corresponding augmented matrix. Solving this, you would add 3 times equation 1 onto equation 2 to yield this equivalent system of linear equations. Now, at this point, this also has a corresponding augmented matrix. Notice again that on the left we observed that there consequently need to be two free variables, say x3 and x4, in which case we can deduce that x2 is equal to 2 minus 1.4x3 minus 1.8x4. However, if we did not have the equations and only the augmented matrix, we still could have gotten from the first augmented matrix to the second augmented matrix by adding 3 times the first row, that is, adding each entry of the first row multiplied by 3 onto the second row to get that same matrix. Now, of course, we have to understand how to interpret that new matrix, but that will be in the upcoming topics. As a side note, if we were to find a solution to the system of linear equations corresponding to this augmented matrix, we would get the following vector: x is equal to negative 0.2, negative 0.6. Well, interestingly enough, what this means is that negative 0.2 times the first column vector, 1, 4, minus 0.6 times the second column vector, 3, 7, equals the target vector, negative 2, negative 5. Thus, we are literally solving two problems, and the problem is much better interpreted in terms of finding a linear combination of vectors equaling a target vector when we use the augmented matrix way to solve such a system of linear equations. Following this shorter topic, there's a lot of information in here. You now understand how to get an augmented matrix. You know that we can begin to perform equivalent operations to what we did with equations, but we can perform those row operations on the augmented matrix. You are now aware that it will be easier to describe and program such an algorithm without the unnecessary variables. And finally, you understand that a solution to the system of linear equations gives the same solution to the question of finding a linear combination of vectors equaling a given target vector. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!